In this video, I'm going to explain how to solve problem number 4. So to start this problem, I'm going to be writing out our knowns and unknowns. So our first unknown is the volume, the total volume, final, and that is one of our unknowns. And then the temperature. Final is also an unknown. And then we know that the initial pressure is 101,325 pascals. And we know that the initial temperature is 298 Kelvin. And then the final pressure we know is 200,000 pascals. And then we also know that the mass of the water is 1 kilogram. And it'll be 1 kilogram no matter how much is in the liquid phase or vapor phase because of the law of conservation. So that'll be the total. And then finally, we know that the moles of water in the vapor phase is equal to 3. Or 0.3. So now we can start writing out equations of things that we want to know as well. So the total volume will be equal to the volume of water in the liquid phase plus the volume of the water in the vapor phase. And then the mass of the water total will also be equal to the mass of the water in the liquid phase plus the mass of the water in the vapor phase. So now, as you can see, we know this mass of the water total, but we don't know the mass of the water in the liquid phase or the mass of the water in the vapor phase. But we can obtain this by using our moles of water in the vapor phase. So we know that this will equal the moles, or the mass of the water in the vapor phase divided by, obviously, the molecular weight of water, which is 18 times 10 to the negative 3rd kilograms per mole. And then now, we are assuming that this is an ideal gas. So we can say that the final pressure is equal to the pressure of the air in the partial pressure of the air, and plus the partial pressure of the water. So now, for this equation, we don't know the partial pressure of air. So that will just be ideal gas law. So that would equal the number of moles of air times R times the final temperature over the volume of the vapor phase. So next, we can try and figure out this partial pressure of water. So obviously this is a partial pressure that we can just use the Arrhenius equation for. So the partial pressure of water is equal to 10 to the A minus B over C plus the final temperature. So now I'm going to try and figure out this volume of the liquid. So we know that the density of the water in the liquid phase will be equal to the mass of the water in the liquid phase divided by the volume of the liquid. And then we can rearrange this so that the volume of the liquid is equal to, from before, the mass, the total mass of the water minus the mass of the water in the vapor phase divided by the density. And now we also know that the mass of the water in the vapor phase is equal to this from before. So it's equal to 0.3 moles times 1810 to the negative third kilograms per mole. So now we are going to try and figure out this moles of air. So we can also show an equation for that. So N air will be equal to the partial pressure of the air initially, and then that times the volume in vapor phase over R times the initial temperature. Now we can split up this even more. The partial pressure of the air initially is the total pressure initially minus the partial pressure of the water. At the initial temperature as well. And then we can split up this volume of the vapor phase into the total volume minus the mass of the water total over over the density. And all this will still be over R times the initial temperature. So finally, moles of water in the vapor phase will equal the pressure of water at the final temperature times the volume in the vapor phase over R times the final temperature. And obviously this will equal our known 0.3. So now I'm going to use all these equations that I figured out and the knowns and write a Python code to solve for our two unknowns. So the first step to solving this problem on Python will be to import this set of tools into our code that has different values for water, different like physical properties for water, like the critical temperature, pressure, volume, and what we're going to use, the vapor pressure. So to import this onto our code, we're going to use git clone command. And I'm going to copy this URL. And that will download this or clone it into our collaboratory right here. So now we want the actual CHE tools section of this. So we can get to that by doing a system path. And we want the CHE tools. As you can see, we have all these text files with our different physical properties. So now to be able to use this throughout our rest of our code, I'm going to import the tools as CHE. Now we need to download these tools for water, since our problem is only going to be dealing with the water values. And then we are also going to need to download SciPy root solver since we know that we're going to be solving two equations with two unknowns. So from SciPy optimize import root. And then finally, we are going to need the constant R, which equals 8.314 joules per mole Kelvin. So I'm just counting all that. So in order to use this root command, we are going to need to define a function to put into here. So I'm just going to call this our equations, and we needed to supply a vector or an array with our unknowns to this function. So I can unpack this and call it our two unknowns, the final temperature and the total volume. So now what we want to return is our two equations. So the first one is the final pressure minus the pressure in the air, the partial pressure of the air, plus the partial pressure of the water. And then our second equation is the moles equation, where the moles of water in the vapor phase minus our moles of water in the vapor well, it's really just minus 0.3, but we can define that as the moles of water vapor desired. So now there are a few initial values that we can define. So the final pressure is equal to 2 times 10 to the 5th, the moles of water vapor desired, as I said before, is 0.3, and then the initial pressure is 101,325, and the initial temperature is 298, and then the moles of the water, the total moles of the water, will be equal to, or total mass, I'm sorry, of the water will be equal to 1 kilogram. And I got all these numbers from our list of knowns from before. Now our goal is to get from these unknowns to our two equations. So to start off, I'm going to enter this moles of air equation right here. So number of moles air equals the initial pressure minus, and now we need the partial pressure of the water at the final temperature. So we can use our CHE tools and get the vapor pressure at the initial temperature. And then all that is multiplied by the total volume minus the mass of the water, total mass of the water, total, over the density of the water, which we can also use the CHE tools for. So that would be rho at the initial temperature. And then all that is divided by R times the initial temperature. Now I can actually make this final equation even simpler by just saying that we want the final pressure to be equal to the pressure desired. And I can just call this our pressure desired. So now the final pressure is equal to the partial pressure of the air plus the partial pressure of the water. And then we can also put in this equation where the moles of water in the vapor phase is equal to the partial pressure of the water and then that times the volume in the vapor phase times volume in the vapor phase, and then all that divided by the R value times the final temperature. Now to get this partial pressure of the water, I can use our CHE tools again and get the pressure at the final temperature, like that. Now there are these two values that we still don't know, the volume of the vapor phase and the partial pressure of the air. So first, to get the volume of the vapor phase, we know that that is equal to this equation right here. So volume of the vapor phase is equal to total volume minus the total volume minus volume in the liquid phase. So now we need to figure out the volume in the liquid phase. So the volume in the liquid phase over here is equal to volume of the liquid phase is equal to the mass of the water in the liquid phase divided by the mass of the water in the liquid phase divided by the density at the final temperature. And then now we need to figure out the mass of the water in the liquid phase. So the mass of the water in the liquid phase is equal to from here the mass of the water total minus our moles of vapor desired, moles of vapor desired times our 18 10 to the negative third kilograms per mole. 18 to the negative third. Now to get this partial pressure of the air, we have this equation right here. So the partial pressure of the air is equal to number of moles of air times R times the final temperature over volume of vapor. Finally, we can use our SciPy root solver to solve the equation, and we have to supply an initial guess. So I'm going to say like 350 for the temperature and 0.1 for the volume. And here are the answers.